Hi, this is Professor Fernandez. Let's talk about class notes G from lesson 4. So in this example, we are considering a mass, 1 kilogram mass, that hangs from a spring with a spring constant K equals 4. And I'm calling it here linear air drag. Again, that's the same drag, force, air resistance, dashpot, all the same model that we've been using in this lesson with C equals 4. And the idea is to find the displacement from equilibrium. So I'm going to use the same model that we have been working with in this lesson, and I'm just going to put in all the parameters. So I have that m equals 1, I have c equals 4, again I'm sort of ignoring the units, I'm assuming they're all SI, and then k equals 4 as well. And then characteristic equation here, replace the orders of the derivative with powers of r, so I get that. And I'm going to try to factor here, but let's see how it works. How about we try r plus 2, and we'll double check that. So r squared plus 2r, that's 4r plus 4. Yep, so that seems to work. So this is going to give us a repeated root. We are going to get r equals -2 and also -2. So we are in the case that we just discussed in the previous video in this lesson. So, you might think, oh, so I have the two solutions, e to the minus 2t and e to the minus 2t. And while that's true, these two solutions do not form a fundamental set of solutions because they're Wronskian to 0. So we talked about in the previous video how what we're doing, and that's down here left over from those markings, what we're doing is that we now have a real repeated root, in this case -2. And the general solution is what it would normally be, that's the first solution, e to the -2t in this case. But the second one is that function times t. So I'm going to go back and erase this here. This is actually not the second fundamental solution. The second fundamental solution that we've talked about in the previous video is t times the first solution. Great, so then this gives us the general solution, c1 e to the minus 2t plus c2 t e to the minus 2t. And that's our answer for this exercise.